The smallest particles that we know, like electrons and photons, follow the laws of quantum field theory, which is the wedding of quantum mechanics and Einstein's relativity, the theory of small things and the theory of fast things. In the quantum world, things are very different from the ordinary world we are used to. In ordinary physics, particles traveling from A to B take the shortest path between the 2 points. For instance, if there are no forces, they just go straight. In quantum field theory, instead, particles do not take a single path. It is as if they take every path they can possibly travel simultaneously. When we look at many particles, on average, it will look like they follow the ordinary, shortest trajectory, although the individual paths were longer. So when physicists predict the probability that particles behave in a specific way, they must add up every possible path. Often they can approximate by starting with the simplest paths, those more likely to be taken. Then they add paths that are more complicated to get closer and closer to the complete and exact answer. You might have expected that adding every possible path, one can eventually get every possible result, every mathematical formula that can ever be written down. Physicists used to expect this too. Instead, a surprising simplicity emerges from these calculations. In some cases, adding hundreds of paths and pages of calculations results in an answer so simple it can fit on a t-shirt. While physicists understand some of these simplifications, many are still ongoing mysteries. As an example, think of an electron in a magnetic field, like inside the cathode ray tube of old televisions. Its behavior is controlled by complicated quantum effects, represented by complicated electron paths. The formulas for these paths involve numbers that mathematicians call transcendental. These are numbers like pi that cannot be found through ordinary algebra. Mathematicians like to arrange transcendental numbers into related families that often show up together. But while some members of these families come along for the ride, some are left out. These numbers mysteriously never show up. Even if they appear in individual paths, they miraculously disappear from the final result. Another example is gravity, which can also be described by quantum field theory, using hypothetical particles called gravitons. Gravitons follow paths that are especially complicated, much more complicated than those of other particles. This has made their behavior very difficult to predict. However, physicists have observed that by using 2 copies of the path of a more ordinary particle, they can predict the behavior of gravitons without ever talking about complicated graviton paths. The trick, called the double copy, is very useful because it enables us to predict the behavior of gravitational waves, helping astronomers understand what they see in new gravitational wave telescopes like LIGO. This trick may have a deeper explanation in string theory, but why it works so well remains an open question. Quantum field theory is astonishingly simple, in ways we are only just beginning to understand. If we can understand why our 1,000-page calculations give such simple results, why they avoid certain transcendental numbers, or let us calculate gravity using simpler theories, then we may discover new principles of mathematics that make our difficult calculations a whole lot easier, and perhaps give us a deeper understanding of the theories that govern our world.